Hi guys, I wanted to start this term with statics review. My opinion is that we can't go further in strength of materials without basic knowledge of statics. So firstly, I will talk about force and moment of equilibrium, and what we know from statics that for a rigid body to be in equilibrium, the resultant of all external forces and moments acting on the body must equal to zero. So this statement is true only if we have all of these equations satisfied. That means that sum of forces around in x, y, and z direction are equal to zero, that sum of moments about x, y, and z axes are equal to zero, and we have several steps. The first one is to identify all external forces and moments on the body. The second one is to separate all forces into two main categories: applied loads and reactions. So take care, applied loads are usually the known forces and moments on a body and are given by a specified loading situation. And we have reactions, on the other hand, are typically the unknown forces and moments exerted on the body by its supports or connection. The third step is to draw a free body diagram, and the fourth step is to write equations of equilibrium. So we have different type of supports or connection. The first one, roller, rocker, frictionless surface. We have force with known line of action, that means one unknown. If we have a short cable or short link, again we have a force with known line of action, and again one unknown. Then we have a collar on frictionless rod, frictionless pin in slot, force with known line of action, again only one unknown. If we have a hinge, pin, joint, rough surface, we will have force of unknown direction, which means we have two unknowns. Fixed cantilever support, we will have a force and couple, which means three unknowns because force is given here of unknown direction. So these were reactionate supports and connections. So here is one example. We have overhang simply supported beam subjected to 3-point load forces. The first one is 15 kips, 3 feet far from support A. Then we have 6 kips, 2 feet far from support B. And we have 6 kips, force 4 feet far from support B. So we need to determine the reaction at A and B if we are neglecting the weight of the beam. So what we are doing, firstly, we need to draw a free body diagram. Since that we have a roller at point A, we will have only one vertical force, AY. Then we will have two unknowns at point B because it is a pin. And we have already mentioned 3-point forces. So the next step is equations of equilibrium. The first one, sum of forces in x direction is equal to 0. Using this equation, we will obtain that Bx is equal to 0. Then we have the next equation, sum of moment about point A is equal to 0, which means we have force of 15 kips times 3. Why 3? Because moment is force times perpendicular distance, and in this case the moment will be clockwise. That means minus 15 times 3. Then we have By, our unknown, times 9 feet counterclockwise, minus 6 times 11 clockwise, and minus 6 times 13 clockwise, again minus, is equal to 0. Using this second equation, we will obtain that By is equal to 21 kips. The third equation, sum of forces in y direction to be equal to 0. We have Ay plus By minus 15 minus 6 minus 6. Using By as 21 kips, we will obtain that our reaction at A, vertical reaction, is equal 6 kips up. So the next are internal forces. And in order to find the internal loading at any point in member, it is necessary to make an imaginary cut on the member at the point of interest. If all external forces and reactions are known or have been calculated, then the internal forces can be found by isolating one of the cut sections and solving the equations of equilibrium. Why we need internal forces? Because this step is important to draw shear moment diagram and the moment of normal forces. And why is important? That is important because we need to determine the maximum allowable stresses, which we will cover next time. So what we have here, figure A, we have simply supported beam subjected to two forces, F1 and F2. We are drawing free body diagram. In pin support we have two unknowns, in roller we have one. This is a free body diagram of beam before cut is made, and then we need to draw free body diagram of beam AB after being cut at C, showing all the internal forces or the internal loads developed at cut. If we are cutting from the left, we will have two forces AX, AY, and one external load or a point load F1. So we need to determine moment, normal, and shear forces. If we are cutting from the right, we need to find the forces from external load F2 and from reaction at point B, BY. So our positive normal forces only if they are in a tension or if they are pulling. If they are pushing, we will have a negative normal force or compression. Then we have these are the typical sign convention for positive and negative internal loads. This is for positive shear, showing the left side of the figure, and the negative shear. Then we have a positive bending moment and negative bending moment. So here is one more example. We need to determine the internal forces at point B, just to the left of the 6 kilonewton load. So we have a simply supported beam, roller is at point A, we have a pin support at point D, and at pin support we have counterclockwise moment of 9 kilonewton meter, and we have 6 kilonewton force 3 meters far from support A. So we need to draw a free body diagram. At point A we have only one reaction, at point D we have two unknowns. The third step is to sum of forces in x direction to be equal to 0. That will give us that force dx is equal to 0. Then we have sum of moment at point D to be equal to 0. That means ay times 9 minus 6 times 6 minus 9 is equal to 0, which will give us ay to be 5 kilonewton up. And we have sum of forces in y direction to be equal to 0. That means dy plus ay minus 6 is equal to 0. Solving the third equation, we will have dy is equal 1 kilonewton up. Now, using all of this information, we will draw free body diagrams of the sections made when the beam is cut at B. And since section AB has fewer forces, we'll use it to solve for the internal forces at B using the equations of equilibrium. So if we are cut left from the force, we'll have only AY, which means that our shear force at point B is equal AY. That means 5 kilonewton. We don't have normal force MB is equal to 0. And moment MB will be AY times 3, which means 15 kilonewton meters. So these are your answers. You can do from the right side also, and you need to get the same answer.